Adaptive Computation LLC, a spin-off company from Caltech. Team capability: Dr. Duang as CEO and CTO, PhD, UCI, in Neural Controls and Systems. Dr. Nam Trang as VP Data Science, PhD in UC Berkeley in Mathematics. Vision: Dr. Duang developed unsupervised learning based off his cardiac eye movements and visual pathways and demonstrated it surpassed human vision system performance with 10,000 distractors, and also facilitates the adaptive feedback mechanism as short-term memory. He invented dynamic and self-supervised learning to enable learning sequential samples as available by itself. Hence, it can update knowledge and create new class if needed to equip self-learning intelligence as long-term memory. During DARPA's AIE IP2, he invented the second order of receptor file to demonstrate it produces the sparse image with 61.5 times intensity reduction while maintaining the object selenity. This enables SWAPC as DARPA IP2 objective goals. Integrating them sets a new direction for true intelligent learning systems. Contribution: Significant contributions of his work include successful development of image-based search engines on desktop and mobile and Raspberry Pi platforms, effective mapping for EVIP to solve real-time moving object recognition based on a single database, real-time learning in operation, and real-time adaptation. Self-dynamic supervised learning to facilitate brain-like learning manner for long-term memory. Several patents are granted. Achievements: For his invention of on-chip processing to improve the cost of NASA missions, he received 2002 Exceptional NASA Space Act Award for the creative development of exceptional scientific and technical contributions for aerospace technology program of NASA, and 2004, 2006, and 2009 Standard NASA Space Act Award and 30 NASA Technical Innovation and Monetary Award. 12 patents and monetary awards. Caltech and NASA are assignees. 3 patents, adaptive computation, 3 pending patents, and 5 provisional patents. He published 115 papers and new technology reports and 3 chapters of books. The problem in the state of the art. Higher resolution color image is more to come to provide an effective resolution of the small object to be detected. It also presents the challenges of current deep learning architectures in SWAPC perspective. There are several technical blocks needed to optimize. One is input space can be sparse. Other can be computing architectures such as in-memory processing architecture and or algorithm. Example, ADC invented the second order receptor file to demonstrate it produces the sparse image with 61.5 times intensity reduction while maintaining the object selenity. This worked successfully, done for the DARPA AIE IP2 program. Hence, implementing bio-inspired sparse imager will enable to benefit the SWAPC and input space for deep neural networks, especially space, drone, and edge computing. High-resolution images can carry effective information, small interested objects, but pay heavy price in processing, particularly deep learning architecture. Reducing data in input spaces enables SWAPC. State of the art. Deep learning statistical data-driven approach requires a huge upfront database, and it also requires more powered computation machine and a lot more time to train. Based off our study, AIE DARPA IP2 program, deep learning performs poorly with resolutions of objects less than 32 by 32 pixel arrays using BDD 100K dataset from UC Berkeley for object detection, classification, and tracking. To enhance its performance, a higher resolution camera may be required, but it will pay very high for this approach. Advancing the state of the art. For space, mobile, and edge applications, size, weight, and power with cost, SWAPC system is one of the key parameters to be considered. Adaptive Computation LLC as the PI role with successful Phase 1 and 2 for DARPA AIE IP2 to show the brain-like intelligent system in pixel intelligent processing. Sparse imager based on bio-inspired technology, namely BISIP2, with 60 times data reduction in intensity remains the salient information as compatible as full color images via the study using BDD 100K dataset from UC Berkeley, based on YOLO and ResNet architecture for object detection, classification, and tracking. Implementing this imager will enable the low SWAPC program. If successful, BISI is expected to replace CMOS color imagers and can work directly with processing units, e.g. GPU, CPU, etc., in application that manned visual monitors is not needed. Examples could be space, drone, and edge platforms. In addition, it enables cybersecurity to encode raw data from hackers. Defense and commercial use. For defense applications, BISI enables low swapC, that is one of the key parameters to facilitate space, drone, and edge computing applications and economically benefits. It will fit in the OUSD RNE critical technology areas, trusted AI and autonomy in space technology where DoD and DARPA are heading. In the commercial arena, BISI can have the vast application to reduce the amount of data processing, for example, self-driving cars, taxi, and etc.